All right. So what we're talking about is this idea of something called the definite integral, and this squiggly kind of S-shaped curve is the integral symbol. It stands for the area between the function, which is in here. This is called the integrand, and the limits of integration, or the interval of integration, is the a to the b. Okay, so the function in here, the dx, is just telling us with respect to x. I mean, it's not really a multiplication. I mean, it is. It implies multiplication. It kind of acts like multiplication. Not for anything we're doing when we work these problems. Kind of like when we had dy over dx. It implies division. It comes from slope, change in y over change in x. But when we did derivative, we didn't divide anything. So it didn't mean divide in that sense. But it came from division, and that's kind of the same thing here. All right. So when we read this as the integral of f of x from a to b, or the integral from a to b of f of x. The dx we don't usually read, but we could say with respect to x if you want to. All right. And what it means is this area between the function and the x-axis. It's always between the function and the x-axis, even though we say the area under the curve a lot. What we mean is the area between the curve and the x-axis, okay? So that was the main thing. Now, as of now, there's really three ways we can find this area. One way would be what we started at the beginning of the year, which would be just to approximate or estimate the area. Like maybe we have a grid system and we count the boxes. Remember when we did that? And we just estimate kind of what that area is. So that'd be one way. The way we are focusing on right now is geometry. So if you get a picture that's just made up of lines and pieces of lines, so you get triangles and trapezoids and rectangles, then we can just use rectangle formulas, geometry formulas to find area. Maybe half circles, okay? So we know the circle formula from geometry. So that's that. Now we will learn, starting tomorrow and into early next week, we'll learn a third method, which is much more powerful. Because for this curve right here, the first two aren't going to work. Well, the first one will always work, but it's not exact, just approximate. And geometry doesn't work to find the exact area. So we will learn how we can find this exact area. Now, understand the comparison to when we learned derivatives. We estimated derivatives, slopes, by just sketching a tangent line and doing the rise and the run. On simple ones, like linear equations, we could do the slope because they weren't curved. So we could do the slopes of lines. But then we had to learn a third way. Well, what about things that are curved? How can you do the slope of those? When you only know 1 point, not 2, and we learned how we could do that. It was called the derivative. Well, so that's kind of a similar process here, how we're going to do this. All right, so that's coming up in the next couple days. Very excited about that. Very exciting days tomorrow and Monday. Hopefully you'll all be here. I hate the fact we got a 3-day weekend in between them. I don't hate the fact we have a 3-day weekend. I hate the fact that it happens to come when it is. Well, or we could get together on Friday and Saturday too, and just do it then. All right.
See, I'm going to be in Hastings,
That's-
so I'm going to be sleeping.
I'm telling you, it'd be worth it, but, well, whatever. All
I'm
right.
gonna give you a list of things.
Okay, you make the videos, and we may or may not watch them.
Yeah, may or may not, that's for sure. All right. Okay, so,
That's perfect.
homework questions.
You didn't drop it.
Homework questions. Yes, 17, 18,
Yeah, and then 19 and 21.
and then 19, 21.
Wow. 23, 25.
Gee, Merry Christmas. Okay, well, hopefully if we do a couple of these, that will take care of some of the others. Now, yes, I was saying to you on 17, 18, on those, it says, in the directions in that section, it says, evaluate the definite integral. Evaluate just means find the value. Okay, definite integral is a piece of area, so it's a number, just like a derivative is a number. Now, we have a derivative formula, but a derivative is a slope. So the derivative at a point, that's a number. Okay, it's a slope. Just like an integral is a number, it's an area. So you're supposed to evaluate that integral using a graph. So you were supposed, that's why he was going around saying, hey, you need graphs here. Now, on some of the simple ones, could you maybe do it in your head? Possibly. But so if we take 17, what did that one say? The integral of
5 and
from
2.
2, yeah, we always read from the bottom up to the top. So from 2 to 5, u du. Now remember, this is the function right here. Now it could be in terms of u or v or t or x. It doesn't matter. But if you prefer using x, then use x. But this is the y equals right here. Okay, so what this is asking for the graph of y equals x. That's what it's looking for. Okay, y equals u with respect to u. But usually we think in terms of x, makes it simple. Okay, so we get this line right here. And we want to go from 2 to 5. So we're looking for this area. So it's a trapezoid. So you just need to do the area of the trapezoid. So we're going to do some more of this today. So there's going to be another set of exercises today like this where I want you to draw the graphs. Draw a sketch of it and then get the area. So now, since this is y equals x, that means this will also be a height of 2. Means this will be a height of 5. So the area of a trapezoid is 1/2. And on our next quiz that we take, there'll be something like this. It'll probably be no calculator, right? So I would like to see you write out your work. Can you do a trapezoid area in your head? Probably. But I would like for you to set that up and show me what you're doing, okay? And the height, remember we said yesterday of our trapezoid, this is like a trapezoid on its end. So the two parallel bases, the B1 and the B2 are there, and the height, excuse me, of the trapezoid is here. Okay, so the height would be 3. So this would be 7 times 3 is 21 over 2, and I would just leave it like that. Some of you found out on the midterm, it's sometimes not worth changing the decimals. Just leave it. Yeah.
So when you draw your graph, you just assume that it's a slope of 1
Well, yeah, because that's what it is. It's y equals x. I mean, it's y equals u. That's the function. If this was u squared, it'd be a parabola. If this was sine u, this would be the sine curve. Yeah, and if you typed in what? X. Oh, thank you. I meant to mention that. Yeah, that is not what I wanted you to do. Now, I may have, I maybe should have said that, but at no point yesterday did I show you how to put this in your calculator, right? And you guys are smart, hey, you got this fancy calculator, okay, let's do it. I get that, I understand. But at no point did I say do that yesterday, did I show you how to do that yesterday. In all of our examples yesterday, we did this, right? We did some examples where we drew stuff like this. So that was my expectation. So, right, let's just do that so we're all on the same page. There will come a time, you know how, and I just did one right here. There will come a time where it'll be okay to go to your calculator and just type in these in. That'll be fine. Remember when we got to chapter 4? Weren't there a lot of problems on calculators where it was a big, messy function? We were doing an observation. It was okay to just do the derivative on your calculator and then solve it, set it equal to 0, and let the calculator do all that work, right? But there's also some where you can't do that, the no calculator ones, where you have to work them out. And especially in the early stages of derivatives, we didn't do that, right? I didn't show you that for a long time. So, yeah, we can do this. I don't know, what number is this one? 21. Here's 21, okay? And the answer is 2 pi. But no, I mean, that was not my intent, and it's not my intent on today's homework either for you to do that. And our next quiz will probably be all no calculator, okay? I'm not sure there'll be any part of it that's calculator. But yes, these definite integrals, we can type in, the calculator will give us what that area is. Now, it is kind of interesting. I think I have a graph here, too. Yeah, here's number 25, I believe. Okay, I wanted to show this as a graph. So what I did on number 25 is I went into, now I didn't intend for you to do this at all, but, oops, I went into my Windows settings. 25 was the integral from 0 to what, pi, I think. Okay, so it was the integral from 0 to pi. And so I just set my x and y from 0 to pi, and then I went in here to zoom fit. And, okay, there it is. So it's pi squared minus 3x squared, or 3t squared. Okay? And then I had it do the integral. Now let me hit escape on that to get the integral out of there. Oh, whoops. I got rid of my scratch pad completely. Oh no, it didn't. All right. But the way I got the gray there is I went here to menu, analyze graph, integral, and then for the lower bound I put in 0 and hit enter. And then for the upper bound I typed in pi and hit enter. And then it shaded it. And it's given me the answer. You can't really see it very well, but it's times 10 to the negative 14th, which is essentially what? 0, right? And so that's what it's telling me there, that area is 0. And you can kind of see, oh yeah, it would be. You got some positive, looks like it cancels out that negative, and so 0 seems kind of reasonable. But again, that's not what I wanted you to do. Okay, so it's kind of cool to see what the calculator could do, but you know, there's other ways we have to be able to do it, and eventually we can do this. Now, to be honest, we rarely do this graph because this is so much faster to just type it in over here. Okay, but it's good to, in these early stages, it's good to kind of understand what it is that we're talking about. All right, so with that in mind, this is what I wanted to see on 17. This is what I want to see on 18 or 19, 21, whatever. Okay, now I wanted to talk about 25 here for sure. What does anybody need to see any more on 19 or 21, or is there something I left out there that you still have a question about? What was 21 the circle one? That was okay. The question came up in the other class: should you know that that's a circle? And I would say yes, you should know that that's a circle. When you see square root of 16 minus, was it 16? Or they wrote 4 squared? 4 squared. Or just 4? It was just 4, okay. So if they write this, and it was from negative 2 to 2, yeah. I mean, that comes from something we did really very early on. We did it with piecewise functions. So if I have this, x, that's a circle. So if I solve that, I get r squared minus x squared, and then I do the square root, we get plus or minus, that's the top and the bottom half. And so if you have something that looks like that, yes, you should recognize that that's a circle. And the plus square root's the top half, negative square root's the bottom half. So if that's on our next quiz in the no calculator thing, yeah, I would expect you to know. And so that's a circle with radius 2. Okay, so it would come up, oops, it would come down, and it would be the top half, and so it would be this area. So the area of a circle with radius 2 is pi r squared is 4 pi, top half, so it's 2 pi, and that's why the calculator here a minute ago was showing the answer to be 2 pi. Okay? But yes, the directions would say to draw a sketch, and I'd want to see that. Okay, let's talk about 25. 25, I just drew that picture of it. And you saw how it looked like the answer was 0, right? It looked like what the calculator was telling us. But what did somebody work this out? Maybe how we talked about it yesterday? Or know what we want to do? What do we need to do with it? Do what? Split them up. Yeah, let's talk about these two things we put in our notes yesterday. One of the things we wrote in our notes yesterday is that if I have a function plus or minus a function, I can split that integral into 2 separate integrals. And then the second thing we learned was this right here, that if I have a constant multiplied times a function, I can pull that constant out in front of the integral. So what we can do on this problem is we can use that fact. So we have the integral from 0 to, what was it, pi? Of pi squared minus 3, is it t? T squared dt. Now, if you want to make those x's, the t's, x's, I don't care. That's fine. But what we want to do is we want to split this. So we want to go, okay, this is 0 to pi squared, minus, now I should put dt there, okay, minus the integral from 0 to pi of 3. Now, what can I do with that 3? I can kick it out front, and so this would be t squared dt. All right, now in the directions they told me that 0 to pi of u squared du was pi cubed over 3. So they gave me this piece of information. Now they have to. We could not do that area. Now remember, u squared is the same as what graph? X squared is a parabola. So what they're just telling me right there is that if I took a parabola and went from 0 to pi, like so, that this piece of area right here would be pi cubed over 3. That's what they're telling me there. We don't know that area because we can't use geometry. We can approximate it and see that their answer is reasonable, but we don't know how they get this. We will in a few days. But right now, we can't use geometry because of that curve, right? So, they're just telling us that. Well, wouldn't that be this piece right here? Wouldn't that be that part, right? That part right there is the same as that right there. T squared, u squared, x squared, all the same thing. So this ends up being minus 3 times pi cubed over 3 right here. So the 3's will cancel, so that ends up just being minus pi cubed, right? So what I have left is this. So how do I do that?
It's just a y.
That's just a number, isn't it? That's just a y equals a number. So what this is let's draw it over here. So that's this horizontal line. These are the ones we did yesterday. So this is a horizontal line at pi squared, and we're going to go from 0 to pi. So it's a rectangle. Pi wide, pi squared tall. What's the area? Pi cubed. So this one is pi cubed right here, minus pi cubed. Answer is 0. That's how you want to work out one like number 25. Okay? All right, so that's where those rules, those formulas we came up with the other day come in. Now, another place where this, and maybe you had some of these, or maybe we get some of these today on today's homework. It might be today's homework a little bit. But let me throw another one at you, because this is something like this will definitely be on the quiz, our next quiz. I mean, this is just the fundamental kind of, we got to shift gears and think back to where we were back in November, right? When we were first learning derivatives and stuff. I mean, this fundamental kind of basic things with notation and those kind of things that we got to understand. So here's the problem. Here's just an example. So let's say I gave you the problem 0 to 3, h of x dx. Well, I think maybe you had one. Yeah, 36. Yeah, that's the one I'm thinking of. 36. It was -2 to 5. And they told you that h of x was -11. Okay, so on 36, they ask you for the integral from -2 to 5, I believe, right? Of h of x plus 1. Now, if this exact problem was on our quiz a week from now, I promise you there'll be some people who will put -10. And you may not want to admit it, but there might be some of you on your paper right now have -10 for number 36. Okay? It is not -10, right? Because what you see is you see the plus 1 and you think, okay, it's just this plus 1, but this is the area, -11. Is this saying just add one piece of area? No, it's saying add 1 to what? The function. Now, there's two different ways you can think about this. There's two different ways you can think about this problem. One way would be what? We just did it. Split it apart. So one way to do this is to take this and go -2 to 5 h of x dx plus the integral from -2 to 5 of 1 dx. Right? So this first one is -11. And what's this one? It's 7. Why is it 7? Because it's the graph of y equals 1 from -2 to 5. So what it is this rectangle that is 1 tall and 7 wide, which makes an area of 7. So this is -11 plus 7, which is -4. So -4 is the answer you want to have in number 36. Okay? Now, does anybody have another way we could think about this? Shifting the graph of h of x up 1. If you think of this h of x graph, now this one's a little harder to picture because it's negative, so that means the area should be below, right? When the area is below, it's negative. So I want to do this as a positive area just so to help you get this. So in general, if I had a piece of area, okay, let's just say I was going, I know this isn't going to be the same numbers, but let's just say I had a problem that went from 5 to 9, and I had this piece of area, and I told you that that piece of area right there was 12. Okay, that black piece of area is 12. Now, if I shift that graph up 3, okay, what have I added? Well, by shifting it up 3, what I've done is now this blue area here, wouldn't it be true that this blue area would be the same as that original black area? Right? By shifting up 3, this blue area would be the same as that original black area. So that blue area there is 12. But what have I gained? I've gained a rectangular piece that is 4 wide and 3 tall, which is 12. Another 12. Well, that's cool. So I've added another block of area, a rectangular. So whenever I shift the graph up, I've added a rectangular block of area. Now it works when it's negative too. Imagine this: if the area was all negative and I shift it up, what happens? Some of that negative becomes positive. How much? Well, a rectangular piece of it, right? However far up I shifted it. So here I had -11. So if I shift that graph up 1, I'm going to add a rectangular block of positive area that's 1 tall and 7 wide. So I've added 7 to that. And so some of that positive will cancel some of the negative, and that's how the -4 ends up being there. Okay, so you have to think of it those ways. So either one of those will be fine. Split it apart and do it that way, or just think of it as a shift up and adding that strip of area. But it doesn't just add 1 to that answer. That's a very common thing people want to do, but it's not correct there. Okay? All right. So those are some of the important issues that we get into with this notation. Now, we talked yesterday about, maybe we should do that just real quick, because yesterday we were going over, whoops, that's not the one I wanted yet. We talked about this idea of an integral. So this area, so Melissa, who was gone yesterday, and anybody else listening, so the area below the x-axis is negative area. So this rectangle is 3 by 2, that's a -6 area. And then the other thing we talked about is if you go backwards, if your integral goes backwards 9 to 7, remember the lower number is supposed to be on the bottom, bigger number on top. So if they're written backwards, it's opposite. So this is a positive area because it's up above, but since we went backwards 9 to 7, the area is negative. So anytime your limits here go backwards, the answer is opposite. Okay, so those were a couple of other issues that we talked about yesterday. So what I want to do is talk about 2 new things today. Well, one's kind of an old thing, but it wasn't in your homework. So this was another thing we put in our notes. So if you want to get your notes out, we're going to do a little bit with this, and this is going to be in your homework, I believe, today. All right, so the first example, this is what we wrote down yesterday. We said the integral from a to b. Matter of fact, let me, I'll just rewrite that Um, okay, so we said that the integral from a to b of f of x dx is equal to the integral from a to c f of x dx plus the integral from c to b. Now, we said that that was really easy to see. I'm going to do two examples here. We said that was really easy to see when you had a function like this and c is in between them. Okay, so let's use some color here. Let's make this be black. Okay, so the area from A to B is going to be black. I know this is hard to do in your notes, unless you've got some colors. Let's let this be red. So the area from A to C is going to be red. And then we'll do blue for the area from C to B. So, all right, so that seems to make perfect sense. So the black area is equal to the red area plus the blue area. Okay, so that seems to be very obvious. But what I said to you yesterday is the C does not have to be in between them. All right, so if I look at another example and I put A here, put B here, and put C out here. Now again, let's let A to B be the black area, right? So there's the area from A to B. Let's let A to C be the red area. And then let's let C to B be the blue area. Now some of you probably see this already, what's going on, but think about this. If you take the red area, which is from A to B, or excuse me, A to C, and that'd be positive. And then what do you notice when you do the area from C to B? It's backwards, isn't it? Because the way this is written is it goes from C to B, but if you look at this, C to B is going right to left. We said that's opposite. So this blue area would be negative. So now we got the red area, which is all of it, plus the blue area, which is negative, would cancel off, and what would you end up with? The black area. Okay? So it's still the red plus the blue still equals the black because of that idea of negative. And it would also work if I had my function cross through the x-axis and I had some negative, some positive. It gets a little more confusing to follow, but it still would be the same. Okay, so the important lesson from this then is that when we look at this formula, what we see right here. Now, some people will prefer to use this formula with the C in between and write it that way because it'll just make more sense to go left to right. A, then C, then B, with C in between. Okay, it'll just make more sense for this number to be in between the two. Okay, but it goes from A to B. Your starting bottom one here is A. Your ending one up here is B. So let's look at an example. This will be something like you'll have in your homework today. So it'll be something like this. And so you might want to write this down. It's up to you. So let's say you'll have given to you something like this. All right, the area from 0 to 2 is 8. And you'll also be given that the area from 0 to 5 is negative 12. And then you'll be asked to find some different areas, but one of them could potentially be this area right here. You'll be asked to find that area right there. The integral from 5 to 2. Now again, keep in mind why we're doing all this stuff. What's this integral business? Remember what it means. It's just notation to mean area. Why do we care about area? Well, we gave the example of position and velocity, right? The area underneath the velocity graph we said was the position, the position function or distance traveled, that kind of thing. So that's at least one reason why knowing these areas, being able to do areas, might be useful. There'll be more. All right, ideas. Anybody just, some of you can probably just look at it and tell me what the answer is right now. Anybody got an idea? 20? I believe it is. Okay? I believe it is. Now, if you're not seeing that it's 20, okay, let's look at it from the formula perspective. Now, one way of doing it with the formula, if we really wanted to do the integral from 5 to 2, it would do this. We would say, okay, I want my integral to start at 5. Okay, I'll just kind of shortcut this a little bit, just put f there. That's kind of like sometimes we just write y prime or f prime. We don't put f prime of x, or we don't put dy over dx. Okay, I'm just going to do this integral. And I want to end my integral at 2. Okay, that's the way I'd be looking at that if I'm using that formula. So I have my a and my b, and then here goes the c. Well, what number would I pick for that? 0, because in both of my integrals up here I have 0. Now 0 is not between 2 and 5, but remember, it doesn't matter. It doesn't matter. So if I want the integral from 5 to 2, I can go from 5 to 0 plus 0 to 2. And if you look at that, that looks just like this formula here. 5 to 2, here's the 5, here's the 2, and then here I put, in this case, a 0. Okay, so now what's the integral from 5 to 0? That'd be the opposite of this one, right? Because this one, 0 to 5, is negative 12, so 5 to 0 is opposite, so that's 12. What's the integral from 0 to 2? 8. 12 plus 8? 20. There it is. Okay, now, some people would prefer to maybe keep that in between. Okay, so somebody in the other class mentioned this, asked if this would work, and it actually does. So some people would look at the 0 and the 2 and the 5, and they'd say, well, how about if I did this? The integral from 0 to 2 plus the integral from 2 to 5 would equal the integral from 0 to 5. Isn't that true? 0 to 2 plus 2 to 5 would make 0 to 5. Okay, that's true. And so then we come back here. Well, 0 to 2 is 8. What's 2 to 5? We don't know. Let's call it x. We don't know what it is, right? That's what we're looking for. Well, sort of. We're actually looking 5 to 2, but that'll be easy. We'll just do opposite. Okay, so we'll just call that x. And then what's the integral 0 to 5? Negative 12. So we'll put negative 12 over here. So now you subtract 8 from both sides, you get negative 20. So that means this integral 2 to 5 is negative 20. So the one I want, 5 to 2, positive 20. So see, so you can make it work that way too. Now, I'm guessing that you guys that just looked at it maybe were just thinking that as a piece of area. You might have been thinking, here's another, and we might have a lot of different ways people are thinking about it. But if I go from 0 to 2, 0 to 5, you might have just been thinking, well, here, this whole piece of area is negative 12, and this piece over here I know is 8. So 8 plus what will make the whole thing be negative 12, right? 8 plus negative 20, right? 8 plus negative 20 will make the whole thing negative 12. But that would be from 2. So this has got to be negative 20. But that's from 2 to 5. I wanted 5 to 2. So you do the opposite. So it'd be positive 20. Okay, so you could do it that way. So there'd be multiple ways to think about that and get that answer. But it is using that same idea. Okay, so there'll be some of that on the homework. All right, now and then last thing is a brand new formula here that you want to write down. And this is called the average value of f of x. We're going to have a formula for what we're going to call the average value of the function f of x. Okay, now this is important because let's say you have a temperature function. You have a function that describes the temperature for the whole year. It might be interesting to know the average temperature. Now when we use do averages, what do we normally do? Add up how many we have and divide by how many we have, right? Well, unfortunately, when you have an infinite number of things, you can't do that. You can't add them up. Now, if you took one temperature reading a day, but you usually you wouldn't do that. If you take the high, you do the average high temperature, and the low temperature, you'd have 365 of those, one for each day. But if you were continually recording temperature throughout the year and graphing that continuous temperature, you would have an infinite number of temperatures, right? I mean, theoretically. So doing the average that way really wouldn't work very well. So here's what it looks like. So let's say we've got this function right here, this blue function from point A to point B. So I got here, so ignore this blue area for a minute. Just look at the blue function. Now, doesn't it make sense? There's a bunch of y values here, right? Infinite number of y values, actually. What I want to know is what y value is the average of all those y values? Well, since we can't add them up, because there's an infinite number of them, but it still makes sense there's an average, right? So I'm going to guess, or you're going to guess, you're going to tell me where to stop my guess. Where do you think the average of these blue y values is? What y value do you think is the average? Up here? Down here? Where do you think? Here's the number. Think it's a little higher?
Just a little more, a little up. Just a little more. Just a little smidgen. No, higher.
How many say higher from here? How many say higher from
Look
here?
how high that one up there. That's way.
How many say lower from here? How many say just stay here?
Sure there. I already don't know.
All right,
No
but
running the fence.
all right, but I think we kind of get the idea that yeah, we're see how low this goes here. Now this is a cubic, so there is some symmetry involved, so you do have a little bit of that happening. Now you notice we do have some areas, so surprise, surprise, area is going to be involved here in a minute. But what we're trying to do is just see what would be reasonable for that average value, okay? And let's see what it is.
Oh, look at that.
We were a little too low. All right. So anyway, but all right.
You wanted to take it all
We-
the way up to 1.7.
I think so.
No, I wouldn't.
All right.
You're saying going up.
All right. All right. Careful. Easy. 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 Yes. No kidding. It's competitive. I mean, ever since Flappy Bird came. out,
Just because I was right.
competition. All right. Now. So look at now. Let's talk about the areas. Now let's talk about the areas. Doesn't it also seem, as you look at this, because you were talking about, hey, there's some way down here and there's some up here, we're trying to balance that out. But do you see that with the areas? If you look at the purple area and the blue area, does it seem reasonable that those are the same? I mean, because what we're trying to do is get this line to be where we have some points up above and some points down below, and kind of that in between. And the same thing is going to happen with the area then. It looks to me like this area kind of offsets this area. And this area here kind of offsets this area. Now, since there's symmetry there, it actually exactly offsets it. I mean, those are exact mirror kind of pieces. It wouldn't always happen that way if you didn't have symmetry. But it looks like that average value, that seems reasonable that would always happen. If you found this y line here that would be the average of your y values, it would seem reasonable that those areas would offset each other. Okay? And we have names for both of those things. So what we can do here is we can write ourselves a little formula equating those two areas, and that's what we're going to do. So we're going to say this, okay, the integral, because the blue area here would be the integral. That's the integral from a to b of f of x dx. That would be the blue area. The purple area would just be the rectangle area. So it would be the height, which we're just going to call our average value, AV. Okay, the height of that rectangle is just our average y value, which is what we're interested in, times the width of the purple rectangle. What's the width of the purple rectangle? Well, a to b, but I can't write a to b. B minus, thank you, yes, b minus a. The width of the purple rectangle is b minus a. Okay, So now, to find my average value, all I have to do is divide both sides by b minus a, and there's our formula. So the average value, we'll put that in our notes here in a second, is, or you can write that in there right now. So under the average value of a function, it is simply that right there. Now notice they call it the mean value theorem for integral, mean meaning average. It is related, actually. It's kind of a cool connection, which we won't get into right now, but it is connected to the mean value theorem for derivatives that we had earlier. Okay, but right now we'll just call it the average value. Okay, that's all we care about right now is it's the average value of the function. All right, so back in our notes, we'll write that, and that is something you need to see because, or you need to basically memorize. Okay, is that the average value of a function, average value of f of x equals the integral from a to b, and usually it's always the average value on a given domain. It's always find the average value of this function from 0 to 20, right? So your integral is going to go from 0 to 20, and then you'll divide by 20, right? B minus a. So this problem, it would be in those packets a fair amount. It's on the AP test almost always. A lot of times it's a temperature of function or it's some sort of thing where you want to find the average value of that, and this is how you go about doing it. Now, to be able to do that, you've got to be able to do the integral. And we said there's a couple ways to do the integral. Approximate its value, geometry, which is what we're doing right now, and then the new way we'll learn to do some of these other ones that we can't do geometry with. Okay? So average value of a function. So there's another application of being able to do an area or be able to do an integral. All right. So I think there's a few problems. I think there's a few problems in the homework where you'll do that. All right. So with that said, boy, that leaves a lot of time. I hate to give you so much time to work.
Let's watch a movie. Oh, that'd be awful.
All right. So here's what we're gonna do. Yeah, you probably get done with the homework. That's cool. All right.
It's Brenda's birthday.
Yeah, it's Brenda's birthday.
Today?
Yeah.
Well, happy birthday.
Happy birthday
Your
to
birthday present is a lot of time to work. So you have no. All right. So London. Oh yeah.
Happy birthday to you.
All right. So the chapter 5. So we're going to change this up here a little bit since you have so much time. I'll give you a little few more to do. But I know. 5.1 on the top line. Obviously, what we want to do here is just finish that line. So starting with 38 onward. Okay. So that's the first part of it. And you can do that part second. I don't care. But from 38 onward in the book. Now, I've got this had a hard time with a packet. I don't know what it's called. Pamphlet, a leaflet. I don't know. It's just a few
It's
pages.
definitely not a
But
happy.
this is the LH in this assignment sheet where you see all this references to LH. And again, it's kind of like that Anton packet. It's just named after the authors of the book I got it from. This particular book's the book we used to use. It was written by Larson and Hostetler.
I know
So
people
that's-
with those last names.
So that's the LH. Okay? Yeah.
Oh, do you think she could help us with this?
Yeah, she wrote the book. Heck, yeah. Now, one thing that you should keep in mind, this always kind of cracked me up, so I started being very careful. I probably should, but that'd be cruel. Well, this packet, everybody, if I don't say this, people assume that it's this page, the front page. But it's not. It says page 289. This front page is page 279. Okay, so you're actually going to go to the second page, page 289. Okay, and I want you to do all 20 that are on here, not what's written on the assignment sheet, but I want you to do all 20. With the only exception being number 7. You can skip 7, and we'll talk about that one separately. But otherwise, we do all 20. Now, what always kind of humored me about the people that would work page 279 is we hadn't talked about any of that stuff. And so it should look really strange, but some people would just work away and just do those problems without any questions.
Would they get them right?
Well, no. And what bothered me about that is they should have been really confused, but it didn't seem to bother them, which made me think that maybe every day when they did their homework, they were really confused, and this was just another day. And I thought, I did feel kind of, and so I was, you know, so I thought, well, that's not good. I mean, right? I mean, sometimes showing what you know is also showing what you don't know, right? I mean, they were so lost they didn't even know what they didn't know. So
I don't even know what
I don't even know what I don't know, let alone what I do know. So I don't know. It was kind of weird, but so anyway. So the first couple on that page, the first 10, all you have to do is set up the integral. So like number 1, I mean, again, this is just real simple. It just says set up the integral. So the function is 3. It goes from 0 to 5. I mean, that's it. I mean, it isn't going to take very long. So on number 1 on that packet, right, they give you the picture. They just want you to write the integral. You don't even have to find the area. Now, when you get to 11 through 20, then those are like the ones we talked about in 17 and 21, right? You're supposed to draw a picture. Supposed to draw the picture. Draw a picture, thank you. Put it note by number 11 through 20. Draw a picture. They'll make triangles and half circles and trapezoids and stuff like that. And then calculate the area. Okay? So that's on this LH packet, 1 through 20. Then also, like I said, in the book, 5.1, do the rest of that line from 38 on. Okay? All right, so you have the rest of the block to do that. So if you've got any questions, because I want to get into the new stuff tomorrow, and I don't want to spend a lot of time going over this, so, you know, check your answers. I got an answer book up here. Ask questions. Card talk, that's velocity, acceleration, miles per hour. She's in the book.
I know, I was saying, but at something. Well, of course I'm talking to myself. No one else will talk to me.
That's a surprise.
The only other person who talks to me is you, Mr. Clerk. How's that make you feel?
Good.
Yeah, that's why I was texting.
Can I go for this?
Yeah.
Say that